Hi everyone, welcome to today's session. Myself Hima, Assistant Professor, Department of Information Technology, SA Engineering College. In today's session, we are going to see the basic concepts of process, which is a topic from the subject operating systems. So we know operating system executes a variety of processes. If it's a batch system, we can call it as jobs, or if it's a time-shared system, we can call it as either user programs or tasks. Many modern process concepts are still expressed in terms of jobs, and the two terms job and process we can use it interchangeably. So basically the system contains n number of processes, and there will be a scheduler program which is responsible for selecting one particular process for execution, and that process will be allocated with the processor. Now let us see what is basically a process. A process means a program in execution. That is, when a user writes a set of instructions to achieve a particular task, we can call it as a program. When the user executes that program, we can call it as a process. So process is an instance of a computer program that is being executed. And the process is having four sections: text section, data section, heap section, and stack section, where text section covers the instructions. Then data section contains the global variables and the static variables for the process. The heap section, it is for dynamic memory allocation. And finally, the stack is for local variables. So when local variables are created, it will be allocated to stack, and once it is out of the scope, it will be removed from the stack. Now let's see the difference between a program and a process. We can say program as a passive entity and a process as an active entity. That is, a program which is just an executable file which is stored in the disk. And the program becomes a process when that executable file is loaded into memory for execution. Then it becomes a process. The process is associated with a program counter which will point to the next instruction that is to be executed. Also, it is allocated with the resources which is required for the execution of that particular process. Then as a process executes, it can pass through these 5 states. A process is having mainly 5 states: new, running, waiting, ready, and terminated. When a process is created newly, it will be in the new state. Once it started execution, it will go to running stage. Then when the process is waiting for some event to occur, it will be in the waiting stage. Then if the process is ready for execution, it will be in the ready state. And once the process finished its execution, it will go to terminated state. So during the lifetime of a process, it will go through each of these states. So this is the diagrammatic representation of how the process moves in between the states. This diagram is called process state transition diagram. So initially when the new process is created, it will be in the new state. And once the process is ready for execution, it will go to ready state. Then when it is allocated with the processor, that is when it is getting the processor, it will go to running state, that is it starts execution. Then from running state, it can either go to ready state or to waiting stage or to terminated stage. There are 3 cases. While running, suppose if an interrupt occurs, the processor has to service the interrupt. It has to execute the interrupt service routine. So what the processor will do is, it will suspend the execution of the process. Then it will go to ready state again. That is, again it is waiting for the processor. Once the processor finish the interrupt service routine, again it will start execution. That is, again it will go to running stage. Second case is that when the process is executing, suppose an IO operation or any event, it is waiting for a particular IO operation or any event, then it will go to waiting stage. So after the completion of that particular event or IO operation, again it will go to ready state. That is, that event has been completed and it is ready for execution. So once it is ready means when it is allocated with the processor, again it can start execution. Third case is it finished the execution. It has executed all the instructions. That is, it is about to terminate. Then the process will go to terminated stage. So these are the different states of a process while it executes. Next, we'll see what is process control block. Each process is represented in the operating system using a process control block or PCB. We can call it as PCB. Every process is associated with a PCB. The PCB stores some important information about the processes. Like the state of the process, it can be ready, new or waiting. Next is the program counter, which will point to the next instruction that is to be executed. Then the CPU registers like accumulator, general purpose registers, which is necessary for the execution of this particular process. Then the CPU scheduling information like priority. Then the memory management information like page tables information, segment tables information. Then the accounting information, for example, the CPU time utilized. Then status, IO status information. That is the status of IO devices required for this particular process, or the list of open files required for the execution of this process. So all these informations will be stored in the process control block of that particular process. And the architecture of PCB, if you are considering the architecture of PCB, it will be different in different operating system. It is not necessary that the architecture should be same for all OS. It can be different. So depending on the operating system, the contents of the PCB will be also changing. So this is an example for a PCB which stores a pointer which points to the process and the state of the process in the process number. When a process is created, every process is associated with a process ID. That is a unique number which identifies that particular process. The process number, then program counter, registers, memory limits, and list of open files, and so on. So this is an example which shows how the processor switches in between different processes. So when a process starts execution, the corresponding PCB will be loaded into the memory. Once it finishes execution, that corresponding PCB will be deleted from the memory. So in this example, we have two processes, process P0 and process P1. So initially, the P0 starts execution. That time, the corresponding PCB of P0, that is PCB 0, corresponding to process P0. PCB 0 will be loaded and it continues execution. In the middle, an interrupt or a system call occurs. Assume that an interrupt occurs. Then the process P0 will get suspended because the processor has to execute the corresponding interrupt service routine. So what the OS will do is, it will store or it will save the state of that process P0 into PCB 0 and it will go for servicing the interrupt. Then after completing the interrupt service routine, next P1 can start execution. So P1 once started execution means first the PCB 1 will be loaded into main memory. Since P1 is executing, PCB 1 should be in the memory. Then again an interrupt or system call occurs. Again the processor will suspend the execution of P1. After completing the interrupt service routine, again P0 can start execution by loading PCB 0. So when P1 is executing, the PCB 1 will be active in memory, while process P0 is executing, PCB 0 will be active in the memory. This is how the processor will be switching in between different processes with the help of PCBs. Now, when you consider a system, there can be a large number of processes. And these processes can be like they are newly created, or they are ready for execution, or they are in a waiting stage. So depending on all these conditions, there can be three types of queues. They are called process scheduling queues: job queue, ready queue, and device queue. Where job queue stores the set of all processes in a system. And ready queue stores the set of all processes which are ready for execution. They are waiting for the CPU. Then the device queue contains the set of all processes which are waiting for any input-output device. All the process will migrate in between these various queues in a system. Now let's see the operations on processes. Here mainly we are considering only two operations, process creation and process termination. First is process creation. When a process is executed, it can create another process. The creating process is called parent process, and the newly created process is called the children of those parent process. And each and every process in the system is associated with a process ID or PID. That will be a unique integer which identifies that particular process. And this child process, in turn, they can create another child process. So this can continue, which will form a tree of process. Now we will consider resource sharing, execution and address space for this parent and child processes. First is resource sharing. There are three cases about resource sharing. One is the parent and child share all the resources. Both parent and child can share all the available resources. Then the children share subset of parents' resources. So parents will have a set of resources. In that the child can use a subset of resource. Then the third scenario is the parent and child share no resources. So they will have a separate set of resources. There will not be any sharing. Next is execution. Parent and child can execute simultaneously or concurrently. That is the first case. Second case is the parent will wait until the child finishes its execution. So once the child finishes, parent can resume the execution. Then third case is address space. The child can duplicate the parent. That is, they will be sharing the same program and data segments in memory. That is the first case. Second case is child may be a different program, so it needs a different address space with all new code and data segments. So they will act as a two different or separate programs. Now let's see one example from Unix. In Unix we can use the system called fork to create a child process. So if you are invoking fork n times, that will create 2 to the power n minus 1 childs. That is the formula for calculating the number of children. So in this diagram, a parent is invoking a fork system call. So fork will return the new, if the call is successful, means it will return the child process ID to the parent, and it will return a 0 to the child process. And the parent is waiting here until the child finish its execution. So you can use exec system call, which will be called after the fork system call to start the execution of newly created process. So here exec is called, and once the child finish its execution, the parent will resume the execution. So this is a tree of process in a Linux system. So here the parent is init with a PID 1 which created 3 child processes. They in turn created another set of child processes so that it becomes a tree. Here we can see that each process is having a unique identifier which will identify that particular process. Next operation on process is process termination. So once the execution is over, the process will get terminated. So that time the child will give all its output to the parent through wait system call. And all the resources allocated by the operating system, they will be deallocated. And parent may terminate the execution of a child process in 4 situations, like 4 cases. The parent can abort the execution of a child. That is, first one is child has exceeded the allocated resources. Second case is the task assigned to the child is no longer required. It has completed all the tasks. It is no longer required. In that case, the parent will abort the child process. Then third case is parent is exiting. So OS will never allow a child to continue when the parent is exiting. So it will forcefully make the child to exit. That is called cascading termination. So in all these cases, the child process will get exited. Now in a system, actually there are two categories of processes: independent processes and cooperating processes. Independent processes are those processes whose execution cannot be affected by the execution of another process. Whereas cooperating process means they can affect or be affected by the execution of another process. So these are the advantages of cooperating processes. First one is information sharing. Suppose you want to share a common file between few processes, it will be helpful. Second one is computation speed. If you want to solve a problem, we can reduce the we can divide the problem into subtasks. Then we can find the solution for each of those tasks simultaneously. So that will increase the speed of processing. Then modularity means we can divide the system into a set of modules like cooperative modules. That will increase the efficiency of development. Then last one is convenience. For example, if a user wants to do multitasking, he can open the same code in multiple windows, one for coding, one for compiling, or one for executing. Like that, multiple tasks he can execute or he can do, that is convenience. So that's all about the basics of processes. Now we'll see some questions from this topic. First question is, suppose in a multi-programming environment, the following C program segment is executed. A process goes into IO queue whenever the IO related operation is performed. Assume that there will be always a context switch whenever a process requests for an IO and also whenever the process returns from an IO. The number of times the process will enter the ready queue during its lifetime is, without counting the first entry. So here we are asked to find out the number of times the process will enter into the ready queue during its lifetime without counting the initial entry. So once the process enters or it is requesting for an IO operation, it will go to IO queue. Then again it will, after completing that IO operation, it will enter into the ready queue, that we know. Okay, so see the program. So the first line is the declaration and initialization. Then second line is a scanf statement, which is to read the value of the variable x, that is an input-output statement. So here an IO operation is required, that is reading the value of x is required. So the process will go to IO queue. So here the process will go to IO queue to complete this IO reading operation. Then, so that is, after completing that IO operation, it will enter into ready queue. That is the first entry to ready queue. Then next comes the for loop. For I equal to 0, I less than 20, I plus plus. So this loop will be executing for 20 times. So inside the loop again there is a printf statement, which is an output statement. So here also an IO operation is required, so it will go to IO queue. After completing the operation, it will be entering to the ready queue. So this statement, it will get executed 20 times. This statement will get executed 20 times. So totally 20 plus 1. That is 21 times the process will enter into the ready queue. So here option A is the correct answer, that is 21. Second question, consider a process P running on a CPU, which one or more of the following events will always trigger a context switch by the OS that results in process P moving to a non-running state. So here we have given with 4 options, and we have to find in which of these options the process will be entering into a non-running state. So let's check the first option A. P makes a blocking system call to read a block of data from the disk. So it is concerned with the disk operation and IO operation. So definitely it has to wait till the IO operation completes. So definitely it will go to a non-running state. So option A is one correct answer that makes the process into a non-running state. Then option B, P tries to access a page that is in the swap space, triggering a page fault. We know when a page fault occurs, the OS has to fetch the requested page from disk to main memory. So it will take some time, so definitely the system will go to non-running stage. Then third and fourth options, option C and D, it is concerned with the interrupt. It is not necessary that whenever the interrupt occurs, the process will get, the running process will get suspended. So sometimes it can happen and sometimes it may not happen. So here the correct answer is option A and option B. Next question, which of the following process state transition is or are not possible? Option A is running to ready state. A process can move from running to ready state, no issues. When an interrupt occurs, it can go to ready state. Then second option, waiting to running stage. From waiting, a process will never go to running stage. From waiting, it should go to ready stage. So one correct answer is option B. Then the third option is ready to waiting stage. From ready state, a process will never go to waiting stage. From ready state, it should go to running stage. So this is also correct answer. Fourth option is running to terminated stage. Once the process finished execution, it can go to terminated stage. So option B and C are the correct answer here. Next question is, the following C program is executed on a Linux or Unix system. The total number of child processes created is. So here you have to find the total number of child process created. So here there is a for loop, for I equal to 0, I less than 10, I plus plus. If I mod 2 equal to 0, fork. So this loop will be executing for 10 times. And if this condition is true, fork will get executed. So this I mod 2 equal to 0. How many times it can happen? We have to count the time. Like when I equal to 0, 2, 4, 6 and 8, this condition will become true. So that much time fork will get executed. So we know if n times you are calling the fork, it will create 2 to the power n minus 1 child processes. Okay, so here the fork will get executed 1, 2, 3, 4, 5 times it will get executed. That is 2 to the power 5 minus 1. That much child processes will get created, which is equal to 32 minus 1, which is equal to 31. So this particular fork statement will create 31 child processes. That is, the total number of child processes created is 31. The next question, the maximum number of processes that can be in ready state for a computer system with a CPU and CPU is. So here the answer is independent of n. That is, the number of processes can be in ready state. It does not depend on the number of CPUs. So option D is the correct answer, independent of n. That is the number of CPUs. Next question, a process executes the code fork. Total number of child process created is. So 3 times fork has been invoked. And we know if you invoke fork n times, 2 to the power n minus 1 child processes will be created. So here 3 times fork has been invoked. So 2 to the power 3 minus 1 child processes will get created, which is equal to 8 minus 1, 7. So option C is the correct answer. So that's all for today. Hope this was useful for you. See you on next video. Thank you.